Okay. It's my pleasure to introduce Ruobing Dong or Ruobing Dong. So many audience here are probably already very familiar with him since he was a Bart Bok Fellow at the Stewart Observatory from 2016 to 2018. Then he moved to the University of Victoria as an assistant professor. So Robin has told us that he's very willing to schedule individual meetings to catch up with old friends here. So let us know if you are interested and we can help organize. So today we'll hear him talking about observational planet formation. So without further ado, let's welcome Robin.
Thank you so much, and it's very nice to see maybe not many faces, but many familiar names in the chat list. So yeah, so I took this photo back when I was in Tucson a few years ago. I think it was at one of U of A's parking lot, if I remember correctly. So it's an ordinary sunny day with blue sky and almost no clouds. So at this particular moment, however, we know there was a plane in the sky. So we couldn't directly see the plane, but it's too tiny and too faint. But the tail left behind by the plane betrays its presence. The tail was a lot more prominent than the plane itself. It not only tells us where the plane was, but it also helps us to characterize a plane, like where the plane has been and where it was going, and even how many engines it had. Look at the two contrails. So in my talk, I will tell a story somewhat similar to this, but instead of how to use contrails to look for planes in the sky, we will be looking for protoplanets forming in protoplanetary disks using a structure they produced in disks. So here's the animation that will show the general idea of how stars and planets form. So we think stars form in molecular clouds as they collapse under their own gravity. So here's a cloud, and we're flying into the center. So at the center, we see a newborn star, and in just a minute, we'll see a planet forming in a flattened rotating disk around the star. There are also jets going on perpendicular to the disk. We don't need to worry about it for this talk. So this disk is called a protoplanetary disk. It is where we think planets are born. And the disk is made of gas and dust particles, and it can go from a few stellar radii all the way to hundreds or even tens or even hundreds of AU. Such disks last typically for a few minute years. So now we're flying into the disk. So in the middle of this gaseous and dusty environment, we see a new planet that is just forming. This planet actually has its own tiny accretion disk around itself. We call this one a circumplanetary disk. This is where satellites may be forming. So protoplanetary disks are the birthplaces of planet. So one thing I want to highlight is the timescale planet formation. So as a reference, the sun is about 4.6 billion years old, and the sun is just an ordinary mean sequence star in the galaxy. Protoplanetary disks, however, they only last for a few million years. At the end, the gas and dust in the disk dissipates. Therefore, for typical mean sequence star in our galaxy, most of the planet formation processes took place in the initial 0.1% of the lifetime of the star. So if we make an analogy to say the sun is a 40 years old middle-aged person, then most of the planet formation process need to happen in the first 15 days of the life of this person. So because planets form in disks, the best way to study how they form in observations is to directly observe them as they are forming in disks. By doing so, we can constrain fundamental parameters in planet formation, such as the location, the time scale, and the local environment in planet formation. Finding planets forming in disk, however, is quite challenging. Now you may wonder, because we know thousands of planets have been found, so how could finding them still difficult? This is because most planets found to date are orbiting around very old stars, billion years old. So this histogram shows the number of planets detected as a function of time, color-coded by detection techniques. So it's clear most planets, well, first of all, it's clear that people are discovering hundreds of or even thousands of exoplanets every year. But it's clear that most planets were discovered using just one of two methods. They're either red method, radial velocity, or green method, transits. These two techniques, they strongly prefer quiet and stable stars because only such stars enable us to easily disentangle the tiny signal produced by the planet from the observation of the stars. Young stars a few million years old tend to be active, so they're not good targets for these two techniques. As a result, almost all stars found to date are orbiting around billion years old sun-like star, and only a handful of planets have ever been found that are still going around young stars a few million years old. Because of this, a new approach has been developed in the past few years in which we use resolved observations of disks to infer the presence of forming planets and to constrain their properties. So the idea is very simple. Planets are gravitational perturbers. They perturb the material distribution in the disk and they generate density structures. So this process is called gravitational disk-planet interaction. So here I'm going to show an animation that will give us the basic idea of how this process looks like. So this animation is produced from a hydrodynamic simulation and will show the surface density evolution in a disk perturbed by a Jupiter mass planet. So the simulation will be in a frame co-rotating with the planet, so the planet won't move. This particular one has a viscosity alpha equals 10 to the minus 3. So let's launch the simulation. You see the planet quickly launch those spiral-arm-like density waves, and then it removes material from its orbital region to open a gap, and that separates the disk to two parts, an inner and outer part. The two gap edges become so-called Rossby unstable, and the outcome of the Rossby instability is the formation of two vortices at the two edges. Those are large-scale as mutually asymmetric structures. Now, the planet is very tiny and faint next to the bright star and the big disk, so it's very difficult to see. But those planet-induced structures in disk, they are much larger physical scale and are a lot more prominent. So if we can detect those structures and convince ourselves they are produced by embedded planets forming in disks, these structures can be the signpost of planet formation. So in a way, that's similar to how we identify the plane in the picture on my opening slide. So now let's ask a zeroth order fundamental question here. What kind of observations do we need in order to detect those structures in real observations? We can address this question from some back of the envelope estimate. So first of all, protoplanetary disks are located in star-forming regions, and the nearby ones are at about 140 parsec away from us. The location of planet formation process is not exactly clear, but we can use the solar system as a reference. The outermost planet in the solar system, Neptune, is at 30 AU away from us. So let's say 30 AU is a characteristic scale. The size of planet-induced structures is usually a fraction of the orbital radius of the planet. So for a planet at 30 AU, we're talking about a few to 10 AU, give or take. And finally, 1 AU at 140 parsec is 7 milliarcsecond. So put everything together, we find in order to detect planet formation signatures in a nearby disk on solar system scale, we need to satisfy two conditions. So first, we need an inner working angle no bigger than 0.2 arcsecond. This is to say we need to be sensitive to what's going on close to the star. And secondly, we need an angular resolution a few tens of milliarcsecond. This is needed because we need to resolve those structures. This angle here is very small. So how large it is? It's about the size of a quarter. If we put it in Phoenix and we try to look at it from Tucson. Regarding the first requirement, one analogy that people often make is this is similar to how we can find a firefly next to a bright lighthouse. We need to turn off the lighthouse first in order to see the firefly. So in disk observations, we need to find a way to suppress the light from the central star in order to detect the faint structures next to the star. This condition is, of course, only needed if we're working at a wavelength in which the star itself is bright. So observations satisfying both conditions were not quite possible until about a decade ago. So in the next few slides, let me show you two examples to highlight cutting-edge capabilities in disk imaging observation. And in each example, I will first show a pre-2010 old observation, then I'm going to compare it with a post-2010 modern day observation of the same disk so that we can see the difference. So here's the first example. This is an HST image of the disk around a star called TW Hydra at H-band, so near infrared 1.6 micron. This image is a total intensity image taken in 2005. So at this short wavelength, near infrared, we're looking at scatter light by micron-sized dust at the disk surface. So in this image, we see a gap at about 80 AU from the star. The primary difficulty in imaging disks at those short wavelengths, optical to near infrared, is how do we suppress light from the central star, because the star is quite bright at those wavelengths. HST does so by putting those wedge-shaped chronograph in front of the star to block the starlight. Because of this, and also the inability to perfectly subtract the stellar contamination from the inner region in the observation, the inner 50 AU or so is not quite accessible in this observation. So if we put the solar system to scale here, the entire solar system, the planetary system, will be smaller than this inner working angle. So now let's see how this disk looks like in today's observation. So here is a VLT sphere observation of the same disk at the same wavelengths on the same scale. And we can see the difference here. So this observation employed a new technique called polarization differential imaging technique. So this image is a polarized intensity image. The reason to take polarized intensity image is straightforward. So starlight is usually not polarized, but scatter light from disk is highly polarized. So by taking an image of the system at one polarization and subtract it from another image at another polarization, we can relatively easily cancel out the contribution from the star, but retain the signal from the disk. So by doing so, the sphere team pushed the inner working angle all the way from 50 AU to 5 AU. They see the outer gap at 8 AU was better quality, and they also discovered a second gap at 20 AU. That's not quite accessible in the previous case. So next, let's move on to another example at a different wavelength, 1,000 times longer wavelength. So this is a sub-millimeter array observation of the disk around MWC 758 at 0.87 millimeter. This is a continuum emission map, so roughly trace the distribution of sub-millimeter sized particles. The beam size of this interferometric observation is indicated here. So this roughly marks the angular resolution of the observation. So the entire disk is resolved by something like 2 resolution elements. So in a way, perhaps we can think of this as an image with 2 independent pixels. So we see 2 emission clumps. The northern clump is brighter than the southern one. That tells us there's some degree of asymmetry in the disk. This is a very helpful information. But with a low resolution image, there's not too much else we can say here. So now, again, let's look at how this disk looks like today. This is an Tecma large millimeter array ALMA observation of the same disk at the same wavelengths on the same scale. We can see the difference here. So ALMA brought us a number of advances in disk observation at sub-millimeter wavelengths. And perhaps the most important one is it gives us an angular resolution about an order of magnitude better than previous best. So with this much improved angular resolution, this is as if we suddenly had a pair of good glasses. We can see the structure a lot better. We see in this disk, there is a cavity at the center, and then there is a broad outer disk composed of a few rings. And on top of the outer disk, there are 2 emission clumps, and the northern one is bigger than the southern one. So all these structures, newly discovered structures, will enable us to infer what kind of planets may be forming in this disk, as we will see later. So TW Hydra and MWC 758 are just 2 examples. So by now, a few hundred disks have been imaged with similarly high angular resolution and sufficiently small inner working angle to enable structure detection. So here are some galleries of disk images. So in most of them, we see structures like spiral arms, gaps, and symmetries. As mentioned before, this field is very young because none of these observations were quite possible until about 10 years ago. But at the same time, the field is booming right now. So this plot, this is a very interesting plot, made by Lincoln van der Mare. So this plot shows a fraction of papers on planet formation and protoplanet disks in all of astronomy papers as a function of time in the past 30 years. You can see before 2000, the number was hovering at a fraction of a percent. This is mostly a theoretical study, I would say. Then starting 2000, the field took off. And then we are witnessing a tenfold explosion of the field in the past 2 decades. This increase is largely driven by observations, and particularly resolved observations of disks. All right. A whole bunch of disks have been imaged, and they all have structures. Now, the big question is, are these structures produced by planets? And if so, what can we learn about those planets forming in disks? To address this question, let's compare observed disk structures with what we think planet-induced structures should look like. If observations match theoretical expectations, at least we could say it is possible that observed structures are produced by planets, and by comparing the two, we could constrain planet properties. In the simplest case, let's say we have a planet, we have one planet on a circular and coplanar orbit, we may expect to see at least 3 structures. They're density structures, kinematic structures, and temperature structures. So in the next few slides, I'm going to explain those signatures and compare observed disk structures with simulation. So first, density structures. As we already saw in the movie, a planet can produce spiral arms, gaps, and azimuthal symmetry, so vortices. So here we have 3 observations of the same disk, MWC75A, as 3 different wavelengths on the same scale. The first one, the left one, is a sphere in infrared scatter light image, which shows 2 spiral arms in a near symmetric configuration at tens of EU. As discussed before, scatter light, we're tracing starlight being scattered at the disk surface by micron-sized dust. And now these 2 images in the middle and right, they are continuum emission maps at 1 millimeter and 1 centimeter taken by ALMA and Jansky Very Large Array, JVLA. The middle one, we have already seen it. It shows a cavity, an outer disk, and 2 emission clumps. However, only the northern millimeter clump has a centimeter counterpart in the JVLA image. The southern clump doesn't quite have its counterpart. This central source in the JVLA image coincide with the location of the star. Now, all these features may be explained by 2 giant planets forming in those disks. And here at the bottom, I'm showing you synthetic observations of the corresponding type. They're produced by hydrodynamic and rate of transfer simulations. So they represent what we think planet-induced structures should look like in real observations. So the first one is a synthetic scatter light image that shows a giant planet in the outer disk on a circular orbit traced out by the green circle, can drive a pair of grand design arms inside its orbit in scatter light with a near symmetric configuration that's similar to what we see in the real image. And then the same planet opens a deep gap and triggers the Ruobing instability at its inner gap edge. This Ruobing instability produces a vortex which collects some millimeter sized particles, and that produces the emission clump at millimeter wavelengths. Then a second planet, giant planet, is invoked at 35 AU, and this guy also opens a deep gap, and this time triggers the Ruobing instability at the outer gap edge, produce a vortex, and again trap some millimeter sized particles, and that produces the second emission clump, ALMA emission clump. However, only the northern vortex is good at collecting centimeter sized particles, which is why we see it in the JVLA image. The southern vortex in this simulation is already in the process of decaying, so it doesn't quite trap centimeter sized particles as well, which is why we don't quite see the counterpart here. Okay. As you can imagine, there's an ongoing effort to search for all these predicted planets So some candidates have been found, such as this one in Kevin's LBT observation. Meanwhile, the niche of this candidate and other similar candidates are still under investigation. So this is candidates here outside the two spiral arms. All right, in addition to density structure, a planet can also gravitationally perturb the gas motion, and these non-Keplerian gas movement may be probed in molecular line emission observations. To see what these kinematic signatures are, let's look at some kinematics. So here is a face-on view of a disk, the star is at the center, and here is the edge-on view, the star is on the side, and we have the disk midplane here. Now, in a smooth laminar disk with no planet, the kinematics is very simple. All the gas does is Keplerian rotation around the star, right? Now, if we add a planet into the system, the gas will be doing something in addition to a simple Keplerian motion. So first of all, the planet may assemble a circumplanetary disk around itself. In this mini disk, the gas goes around the planet instead of the star. And then the planet can drive density waves, spiral density waves. And when gas crosses these density waves, their velocity will be perturbed. And finally, if the planet is massive enough and open a gap, then the planet can drive a motion called a meridian circulation inside the gap and at the gap edges. All these red motions are non-Keplerian motion, and if we can detect them, we may infer the presence of a planet. So here is one example of planet-induced gas motion in a real disk. So what we're looking at is something called channel maps in CO emission observation. So we have real observations on the top and simulations at the bottom. So when a CO molecular makes a jump from a high state to a low state, it emits a photon. And this photon has an intrinsic frequency. But if the molecular is moving along the line of sight, this photon will be Doppler shifted to a different frequency. Therefore, by measuring the frequency of the photon, we can infer the line of sight velocity of the emitter. Using this principle, each panel here traces the distribution of gas moving at a certain line of sight velocity with respect to the star. For example, in the first panel here, we're looking at emission from gas that is redshifted, so moving away from us at 0.4 kilometer per second. In the second panel, gas is moving at 0.7 kilometer per second, so on and so forth. When there's no planet, the expectation from a simple Keplerian motion in channel maps is two pairs of smooth swings, as we see in the first two panels and the last two panels. But in the middle panel, we see the northern branch of the emission has a interesting kink, that's what people call them, a little zigzag shaped feature. This zigzag feature is not explainable by a simple Keplerian motion. And to explain this feature, people invoke giant planets. So in this simulation here, Pine et al. Found if you put a 2 Jupiter mass planet, this planet can perturb the velocity of the gas and reproduce this kink structure. So this observation has been taken as an evidence of giant planet in the disk. So in addition to density and kinematic structure, planet can also produce temperature structure. And here is an example. So this work is done by my research assistant, Drew Mooley. So the story is very simple. So here is a gas surface density map. A planet drives some spirals. The spiral has high density with respect to the background and thus higher pressure. So when gas move into the spiral, they get compressed. And as long as the disk is not isothermal, gas will be heated up to a higher temperature due to PDV work. So here is a map showing the gas temperature perturbation delta T at 3 scale heights above the midplane. This is where we think CO emission may come from. So spirals are hotter, at least the spine of the spirals are hotter than the ambient environment by a few Kelvin or 10 to 20%. Interestingly, those spiral-shaped temperature perturbation have been seen before. The right panel shows a real temperature perturbation map in the TW hydro disk. So we see positive and negative delta T at the level of a few Kelvin or 10 to 20%, and more importantly, in the shape of spiral arms. So perhaps those are temperature structures produced by planets. All right. We have seen examples of structures in disk, and we see a disk-planet interaction may be able to reproduce them. So now, assuming that's the case, what do these observations teach us about planet formation? Well, I think there are two basic things we can do here. So first, we can constrain the properties of planets in individual systems. And once we have a large enough sample, we should be able to say something about the statistics of planet formation. So let's talk about property of planets in individual systems first. Intuitively, you may expect if the observed structures are produced by planets, then the morphology of these structures should depend on the planet, should depend on the property of the planet, right? If we change the mass of the planet, for example, or the orbit of the planet, we expect the disk structures to change accordingly. Therefore, by quantifying the relationship between the two, we can infer the properties of the planets from observed disk structure. So here is an example. How do we constrain the mass of the planet if it can open multiple gaps by mirroring the property of the gaps? So in this animation, we'll see the dust surface density evolution driven by a planet again will be in the frame co-rotating with a planet, so the planet will not move. The disk has a low viscosity, alpha is 5 times 10 to the minus 5. So let's start the simulation. We see the planet quickly excites a bunch of waves and open a bunch of gaps. These gaps are opened due to the dissipation of density waves. This is different from the previous simulation we see. In this case, we have a low viscosity environment. Therefore, the dissipation of every density wave leads to the opening of a gap. In the previous example, which has a much higher viscosity, all these density waves are dissipated due to viscous dissipation right at the place where they're excited. Therefore, in this case, one big gap is open around the planet's orbit. Okay, so back to our new simulation. So out of all these gaps, let's pay attention to two particular ones. These two gaps are on the two sides of the planet's orbit. They sandwich a ring of dust in between them, and then together with another two dust rings on the inner and outer side, we're looking at a very characteristic triple ring and double gap structure. Now, if we repeat the same simulation, fixing everything else, but change the planet mass, we expect to see the gap configuration to change accordingly. Here we have 5 simulations, and the planet mass increases to the right. So in all cases, each planet opens a bunch of gaps, but clearly to the right, the gap system becomes more compact. Specifically, the separation between the two gaps on the two sides of the planet orbit shrinks. We can fit this separation delta as a function of planet mass MP and a few other parameters about the disk. Now, this fitting function provides a way to infer a quantity that we're very, very interested in, planet mass, from a quantity that we can measure from observations, separation of the gaps. Now let's apply this relation to a real system. So this is ALMA observation of a disk called HD 169142. It has many gaps and rings, and specifically in the outer disk, we see this very characteristic triple ring and double gap structures. If we assume they're produced by a planet whose orbit coincides with the middle ring, we can then, practically use a ruler. You can measure the separation between these two gaps, and that's delta. And then if you think other parameters that are related to the disk, this relation will help us to infer the mass of the planet. Turns out it's about 10 Earth mass, so it's a mini Neptune planet. And here is a synthetic observation of a real simulation. If we put this mini Neptune in the disk model, it can indeed drive structures and produces triple ring double gap structure. All right, let's move on to talk about statistics. So here is a general idea. It's very simple. So let's say we have a sample of disk and we go out and image all of them. We may find spirals in some disks and gaps and asymmetries perhaps in some others. Now, in every disk with structures, if we assume they're produced by planets, we can apply correlations similar to the example I just introduced to infer the property of the planet, particularly its mass and orbits, from the detected disk structures. And once we've done that for all the systems, we can put the information together and form an opinion on what kind of planets are forming in this sample. So let's give a specific example. There are roughly 24 known single Herbig AB star within 200 parsec. So this is a volume limited sample. Herbig stars are progenitors of mean sequence star with masses higher than, let's say, 1.5 solar mass also. So here's a sample. And there are 24 of them, and 10 of them have been imaged in scatter light. And here are the images. All of them show structures, and specifically, 5 of them show spiral arms. You see these 2, they show a pair of grand design arms, and these 3, they show smaller arms with lower contrast. Previously, we have seen that giant planets can produce spiral arms in scatter light. Now, if we make a bold assumption, these spiral arms are produced by planets, then the sample immediately give us the following statistics. At least 5 out of 24 or 20% of intermediate mass stars are busy forming giant planets at 10 to 100 eV. This number is, of course, due to small number of statistics, and the assumption we made on the way that all these spiral arms are produced by giant planets is, of course, debatable. But this example illustrates the power of using large samples of disk observations to constrain planet formation. So planet formation theory generally have, it's difficult to predict the outcome of planet formation in a specific system, but a good theory should be able to explain statistics like this, like why intermediate mass stars like to form big planets. Okay, observing planet-induced structures in disk can help us constrain the properties of planets in individual systems and probe the statistics of planet formation. All this is good. However, everything here builds on a big assumption. Assuming these structures are produced by planets, is this a valid assumption? Are we sure? It's probably not a surprise to you that we think not all disk structures are produced by planets. Alternative hypotheses have been proposed to explain disk observation without planet. At the moment, in most cases, it's still hard to tell which mechanism is actually working. That said, in some cases, nature offers enough clues that makes us think the non-planetary mechanism may actually be more likely. So here I have a little story about a binary protostar system called ZCMA. This image here is an near-infrared scatter light image of the system. It's a binary system. There are 2 stars, although they're fairly close to each other. They're 0.1 second away. The disk has a 1-arm spiral, or maybe we call this a streamer, almost 2 arcsecond long. This streamer has been known for a long time, and its origin has always been a mystery. So we imaged the system with ALMA in dust continuum emission, and this is the resulting image. We saw the counterpart of the near-infrared streamer, although only the part close to the binary, you can see here. And then we found a point source at 4.2 arcsecond away from the center, and almost exactly along the extension of the streamer. You can put everything together here. So we're not too sure about the nature of the source, so we went ahead and imaged the system again at a longer wavelengths using the Jansky Very Large Array. So here is a 7mm continuum emission map. The source is recovered at 7mm. It seems faint, but nevertheless, it's still a 5-signal detection. So putting all this observation together, we form a hypothesis that maybe we're witnessing a rare stellar encounter in the DCMA system. This source is likely a young stellar object that has just performed a flyby of the disk, and the streamer has little to do with planets. So here's a hydro simulation of the flyby event. The left animation will show the event in a face-on view. The flyby star is going to come in from the lower right corner. It is on an orbit inclined by 45 degrees from the disk, although we couldn't quite tell from the face-on view. So as it comes in, you see the disk is dramatically perturbed and 2 large-scale spirals are produced. In this view, the 2 spirals are roughly symmetric. However, if we look at the system from adjunct, we'll see As we'll do in the animation on the right, we'll see the two are quite different. The flyby object will again come from the lower right corner. So let's play it. This guy comes in and perturbs the disk. You see the two spirals are very different. This one pointing to the intruder is being lifted above the disk plane, and the other spiral on the opposite side is embedded in the plane. So that's a key difference. And this difference will cause a big effect in observations. This spiral pointing to the intruder is illuminated by the central star much better than the other arm, which is in the disk plane. So indeed, if we produce synthetic observations of the simulation, as in the middle bottom panel, we'll see only one spiral will be visible as it is pointing to the flyby. The other spiral on the other side is not quite visible. And overall, the simulated structure is fairly consistent with what we see, a one-arm spiral pointing to a point source at a distance away. So this point source so far hasn't been detected at other wavelengths, so we're not exactly sure its nature. We suspect it is either a very young stellar object with most emission at long wavelengths like some millimeter, or it may be a star with an edge on disk. Okay, disk structures in some systems may not have much to do with the planet, and therefore those structures cannot help us constrain planet property. So how do we know which observed disk structures are produced by planets? The most convincing way is, of course, to directly look for the predicted planet. At the beginning, I mentioned that finding planets to forming disk is very difficult. That said, a huge amount of resources have been invested to look for them, and there have been some successful stories. The best example to date is the PDS-70 system, as you probably know. So here we're looking at the PDS-70 system. The two panels on the left shows scatter light and millimeter continuum image of the PDS-70 disk, in which you see a big cavity, 60 in radius. So theoretical models have long predicted that those big cavities may be produced by multiple giant planets that are working together to open a big common gap. So the middle two panels show synthetic observations of cavities opened by multiple planets. They look fairly like the observations. And now the right panel shows that two planets have been discovered inside the cavity. The background is a scatter light image of the disk, and the blue inset is the scatter light. The blue inset is as the H-alpha detection of PDS-70 BC by Hafner et al. The circumplanetary material around the northern planet have also recently been detected by ALMA, as shown here. You can see this point source. So in the case of PDS-70, we can say that the planet hypothesis has been confirmed. In cases with known planet, we could start playing the inverse game to compare the expected properties of the disk structures with observation. By doing so, we could calibrate disk-planet interaction models, so to speak. And the knowledge we gain this way can be used to refine our planet hypothesis in systems we are not yet able to detect a planet. So apart from PDS-70, there are a handful of planets being found in other systems. One of them is in the CI tau system. So the left panel here shows the ALMA continuum image of CI tau disk, which has a number of gaps and rings. This disk has a planet, although it might not have too much to do with all these rings and gaps. So the middle panel shows the radial velocity curve of the star, in which John Screw and et al. Infer the presence of a hot Jupiter. This planet is massive, 12 Jupiter mass, and has an orbit with an eccentricity of 0.25, a semi-major axis around 0.1 AU. So we're talking about regions very close to the star. This massive planet is going to evacuate the inner disk and open a deep cavity with a size a few times its semi-major axis. Therefore, in theory, we expect the CI tau disk to be, like a transitional disk with a cavity, and its near-infrared axis, which come from the innermost region, is supposed to be missing. However, the SCD of the system, as we see in the left panel, shows quite prominent infrared SCD on top of the stellar photosphere. And there's nothing like a transitional disk like SE, which you would expect to see an infrared dip. So does this pose a challenge to the theory? Did we get things all wrong all this time? So we looked into this by quantitatively checking whether the presence of the planet is consistent with SED. We run hydro simulations putting the planet in the disk. Indeed, the planet does open a big and eccentric cavity, about 0.3 AU in radius, and the cavity is almost 3 orders of magnitude depleted in gas. So it's big, quote unquote, big and deep. However, assuming a micron-sized dust is depleted by the same factor as a gas, so they're well coupled, such a cavity is actually not quite sufficient to suppress the near-infrared excess. So the 3 colored curve here shows the 3 SED curves for different eccentricity of the planet, allowing certain uncertainties. So all of them shows a healthy amount of near-infrared excess. As it turns out, the CI tau case actually provides a support to our understanding of how disk planet interact. Further investigation show that transitional disk-like SED is only indicative of the so-called warm Jupiters on AU scale instead of hot Jupiters at 0.1 AU scale. Cases like PDS-70 and CI tau are nice, however, they're quite rare. Therefore, to answer this question, are structures produced by planet, we need to develop indirect avenues to test the hypothesis without finding the planets themselves. So next, I'm going to introduce a few recent developments on this topic. First, we can measure the pattern speed of the structure and use that to infer the location of the planet. For example, planet drive density waves and in disk, and they correlate, waves correlate with the planet as we see in this movie. Therefore, if we measure the pattern speed of the spiral, we could figure out the planet's semi-mirror axis using Kepler's third law. Here's a scalar image of MWC-75A taken in 2015. We went back, well, actually, Bing Ren at Caltech went back to the disk after 4 years and took another image of the system at the same wavelength. And here's a new image in 2019. So ignore the change in the illumination pattern for now. Here's a simple question: have the spirals rotated? It's hard to tell by eye. From theory, we expect a planet at 100 AU or so. So we're talking about an orbital period of 1,000 years, or 1 degree of rotation in a few years. Nevertheless, after careful analysis, Bing concluded that they are rotating, those spirals are rotating at a rate of roughly 0.2 degree a year. It's very tiny, but still measurable. This pattern speed corresponds to an orbit of the driver as shown here. This is roughly consistent with the theoretical prediction of driver on the outside of the spiral. Spirals have also been found in many other disks. We can test whether they're induced by planets by asking the following questions: how would planet-induced spirals look like in other tracers like millimeter-sized dust? And are theoretical expectations consistent with observation? So my wonderful student, Jessica Speedy, is trying to answer those questions. So she uses numerical simulation to obtain the spatial distribution and temperature of millimeter-sized particles, as shown in these 2 panels. With density and temperature, she can simulate how this disk will look like in ALMA observations. What she found is spirals induced by roughly Saturn-ish mass planets are detectable using ALMA under reasonable condition, a few hours of integration time. And spiral arms are easier to detect in adiabatic disks than in isothermal disks, as the detectability is boosted by the enhanced temperature in the adiabatic disks. So she's right now trying to compare theoretical predictions with observations of those disks that have been claimed to have planets and to see whether the theory agree with the observations. So far, I have mostly focused on how planets produce structures in the 2D disk plane. However, planets can also produce structures in the vertical dimension, and if we have ways to detect those, we open a new avenue to test the planet hypothesis. So together with Ming Kai, whom I'm sure many of you are familiar with, my student Jiaqing Li has studied the vertical distribution of dust at edges of gaps produced by planets. So the left panel here shows the meridian circulation inside the gap opened by a planet. So the planet pushes the gas out along the disk midplane, then the gas rises to the surface outside the gap before it comes back into the gap and falling towards the midplane. The right panel will show the density of millimeter-sized particles in the meridional plane, so radial and vertical direction. If there's no planet and there's no turbulence, of course, dust will settle to a thin layer at the midplane due to gravity in the vertical direction. But if there is a giant planet, dust at the gap edges can be puffed up vertically by the meridian circulation. Therefore, the dust rings at the gap edges will develop a finite thickness, and it is actually possible to detect this vertical structure. So here's a schematic of a dust ring at face on. Now, if we tilt it, if the ring is flat, it will just look like this. It will just be squeezed along the minor axis and become an ellipse. However, if the ring has a finite thickness and is optically thin, the line of sight going through the edges will penetrate a thicker layer of material than the line of sight going through the minor axis. As a result, the two edges along the major axis will look brighter than the two along the minor axis. This is very subtle. We're talking about a few percent difference. Still, with ALMA, this may have been observed. The right panel here shows the reobservation of HD 163296. The two panels shows the same data but with different stretch. The middle ring here, as we can see, is brighter along the major axis than the two edges along the minor axis. Perhaps this is a sign of finite vertical thickness puffed up by dust, puffed up by a planet. Okay, so to conclude, in observational planet formation, we look for and characterize planets forming in disks using planet-induced disk structures, just like how we find planes in the sky. Thank you very much. And happy to take questions.
Thank you, Robin, for the very interesting talk. So if you have any questions, please raise your hand. So there were several comments. Okay, we have a question from Kathleen.
Hey, thanks. Really interesting work. Can you go back to the previous slide with the RZ disk dust distribution? Can you talk a little bit more about this simulation and what's been done here?
Right. So those are 3D 3D simulation using Fargo 3D. So they're both dust and some millimeter sized particles there. It has a viscosity, I remember, a little bit less than 10⁻�3. Yeah. And there's a
okay. So yeah. So that these are two fluid simulations.
Correct. Yeah.
With a single grain size.
That's right. Yeah.
Okay, and so you start off with a vertically settled distribution, and then this is for a planet that's what, a Jupiter mass, 5 Jupiter masses. What's the?
Right. So this one looks like a Jupiter, but it's actually a Saturn mass planet. Yeah.
Saturn. Okay. So what is it in thermal masses?
In thermal mass, I believe it's already about thermal mass. Yeah.
But not by much, I guess, if it's only Saturn mass for typical disk properties. I'm just sort of surprised at the degree of excitation that you're showing there.
Right. So if we put a super thermal mass planet here, it turns out the gap will be too wide, and the concentration of dust as a ring will be too far away from the planet, and the puffing up effect is actually, at least if we try to simulate the observation, the puffing up effect will be actually less. So it looks like not like, I guess it's not monotonic. It's not like a bigger planet would have a more prominent puffing up of the dust rings.
Okay, thanks.
We have another question from Leo.
Hi, yes. Hi, Robin.
Hi.
Thanks for the talk. So I guess I have a question, but also a follow-up comment on Gately's point. I think here there's a substantial puffing up, but what's the actual dust to gas density ratio of those substructures? Is is it actually meaningful, or is it just much lower than the initial, I guess, 1%?
Right,
Yeah.
right. So, right. So I didn't explain this figure in more detail. So the quantity plotted here is actually dust to gas mass ratio. So the region, close to bright yellow or close to white actually has a dust to gas mass ratio, let's say on the order of 1% or so. So
I see.
Yeah.
Great. So, going to my question, you mentioned before, I guess, that you're working on a project where spiral excited by a Saturn mass-like planet are more prominent in adiabatic, with an adiabatic equation of state, if I recall correctly.
yes.
So how this conciliate with the work of, for example, Miranda and Rafikov, where I think they show it is true that they explored different cooling rates. So I guess in the limit of purely adiabatic, that may be also in agreement with their work. But I remember that for the wide range of different cooling rates, the spiral waves were actually really weak in comparison with the isothermal case, right? So
you're exactly right. If you're looking at the surface density contrast, then adiabatic disks do have weaker spirals. But the detectability of the spirals in millimeter observations is determined by two factors: temperature and surface density. So adiabatic disks have weaker surface density spiral, but their temperature enhancement is strong enough to first overcome that weakness and actually make the spirals more prominent than the ones in isothermal disks.
Great. Thank you.
Yeah.
Thanks.
Nick?
Hi, Robin. Thanks for the talk.
Hi.
So I think I remember in PDS 70, there's an asymmetry in the millimeter continuum.
Right.
Brighter, noticeably brighter on one side than the other. And I was wondering if the modeling has reproduced that and if it gives you any constraint on alpha in that disk.
That's a good question. I have to confess, I don't recall modeling work specifically targeting this particular asymmetry, although asymmetry symmetry in general on top of dust rings in transitional disks have been thought to be a vortex triggered by the Ross-Waring instability. I'm not too sure. Yeah, I don't know whether this particular system have been modeled in that way. Yeah.
Okay, thank you.
Sure.
Kelly, you still have your hands up. So do you have another question? Or
No, sorry, I forgot to take it down.
no problem. So any other questions? Okay, if we don't have any other questions, so let's thank Ruobing again. And if you can unmute yourself and applaud, it would be nice.
Thanks.
Okay, thanks everyone's coming.